Today I am going to discuss about carbon dioxide molecule. Let us draw the basic skeleton. When we go to determine the number of valence shell electrons that are available for this bonding, carbon has 4, oxygen has 6, 2 oxygen atoms, altogether 16. Now I am completing the octet of 2 oxygen atoms. For that I have to spend all the 16 electrons. That means no lone pairs available on this carbon atom. In this carbon, it has 4 electrons so far. It needs another 4 electrons to complete the octet. We can get those 4 electrons from these 2 oxygen atoms. This will result 2 double bonds. Now this is the completed Lewis structure for carbon dioxide molecule. Now we will determine the charges. I put numbers 1, 2, 3. Anyway, these 2 oxygen atoms are identical. No need to calculate the charges, that means formal charges for both oxygen atoms. We should get the same result. O1, O3, C2. Now I am writing the valence shell electrons. Then I am counting the number of electrons belong to only the oxygen atom. 2, 4, 6. Double bond gives 2 electrons. For this oxygen atom, again 2 lone pairs mean 4 electrons. From the double bond it get 2 electrons, 6 electron total. This carbon 2 double bonds mean 4 electrons. So this means no formal charges. All the atoms are in neutral position. Let us determine the oxidation numbers. In this example, I am using new method. This is more clear for you. These are covalent bonds. Oxygen is more electronegative. Then oxygen withdraw the electron cloud towards itself. This means oxygen peels 2 extra electrons that actually given by carbon. Let us say these 2 attract towards itself. Then it should feel -2 charge. Carbon peel, it lost 2 electrons. It should get +2. But there are 2 double bonds. This side also same. Carbon peels, it lost the 2 electrons given by carbon. These electrons go towards oxygen atom. Then again +2, altogether +4. Oxygen peels, gets 2 extra electrons, then it should peel -2. Then oxidation number for 2 oxygen atom -2, oxidation number for carbon +4. Let us consider the hybridization. First, we will consider the carbon atom, the center atom. Carbon has 2 VACPR units. Then it needs 2 hybridized orbitals. We have to go for the valence shell electrons. 2 electrons in S sub-energy level and another 2 electrons in P sub-energy level. Here what we have to understand is carbon also forms 2 pi bonds. 2 pi bonds and 2 sigma bonds. For 2 sigma bonds, it needs 2 hybridized orbitals. For two 5 bonds, it needs two unpaired electrons. Then this arrangement is not enough for that. I am trying to transfer one of the electrons to p sub-energy level, and then I will take one from S and one from P. This generate sp hybridized orbital. The remaining electrons in p sub-energy level will be used to create 5 bonds. Then I can say the hybridization for carbon is sp. Now let us go to the oxygen. Oxygen has 2 lone pairs and 1 sigma bond. Then it needs 3 hybridized orbitals. Oxygen forms only one 5 bond. For that it needs one single electron. This arrangement fulfills that requirement. I take 1 from S and 2 from P. This will be sp2 hybridized orbitals. This remaining p orbital with the electron will be used to create 5. So you can see 2 lone pairs, and this electron is used to make the sigma. Now let us discuss about the orbital arrangement. This molecule has particular kind of arrangement because it needs to create 2 5 bonds. The central carbon has to create 2 5 bonds with 2 oxygen atoms. And also it has to create 2 sigma bonds. Now this is the orbital diagram for carbon dioxide. I have shown only p orbitals that participate in 5 bonding. The important thing that we have to understand is they are perpendicular to each other. This is the axis and it is on the plane of this whiteboard. This axis used to create the sigma bond using hybridized orbital. And this is this axis. It is also on the plane of the whiteboard but perpendicular to the plane that sigma bonds are creating. You can see this orbital, p orbital on the oxygen atom, and this orbital, p orbital on the carbon, overlap to form 5 bonds. This one and this one. Now these two again overlap, but they are in the plane perpendicular to this axis. And I can draw rough presentation. Say these are sigma bond axis. This is 1 5 bond, 1, and this another one. This I will write 5 2. Each axis are perpendicular to each other. That means 90 degrees. So this orbital, this one and this one, are on the plane of the whiteboard, but these two, this one and this one, are not on the plane of the whiteboard. They are perpendicular to the plane of the whiteboard, but it is very difficult to draw in that way. So I have drawn this way, but mind that they are like this. They should align like this. And this is the sigma. I haven't shown here. This is one of the pi bonds, and this is the other. So they should align as the whiteboard marker, but in this way it is clear that they are p orbitals. Now let us consider the geometry of this molecule. It is not difficult because there are no lone pairs. 2 VSEPR units and no lone pairs mean this would be linear. 180 degrees. So the geometry should be linear.